Our next piece of content is from Patrick Kane. Patrick is with us this morning from Forward Network, and he's the director of sales. And I think this is going to be a particularly interesting subject around the idea of intent-based networking. So what's normal? How do you apply a quant-based model to that on your network infrastructure? And how might we apply that to automation workflows, end-to-end analysis, et cetera, as opposed to just whiteboard type design? So I'm looking forward to this. Thanks for being here this morning, Patrick, and I'll hand off to you.
So yeah, I'm going to speak to you today about intent-based networking. But in Joe's last presentation, I want to just be very clear. What we mean by intent-based networking at Forward Networking is really network verification, network assurance. So we want to provide that assurance through a mathematical model of the network, really to allow your network operators to search, define, and explore their network behavior, really allowing them to be much more proactive and preventative rather than being constantly reactive in the nature of their roles. Before we do that, though, I want to just the fallacy. I don't know if anyone has seen this. It's called The Fallacies of Distributed Computing by Peter Deutsch. So this is a very successful person in the industry, but his time at Sun Microsystems, he came up with this Fallacies of Distributed Computing really to describe the false assumption that programmers new to distributed applications invariably make. So if we look at that, the network is reliable, network is always secure, the network is homogeneous, transport is cost is zero. We know this not to be true. So therefore, what my intent is with my network, well, we have to be able to verify and be assured that it's going to work. If this was all true, we would just know it would work, and we know that's not true. So we have a network operations team to care and feed for the network. So if you look at the day in the life in the week of a network operator and the kinds of tasks a network operator routinely perform, from answering network questions after a breach, responding to a field notice, debugging performance issues or service migration, to executing a change window. These span a variety of areas, from security, audit, performance, change management, just as examples. The variety of challenges that the network operations teams have to deal with is extremely, extremely daunting. Now you put on top of that, what really the complexity they have to deal with on a daily basis, the compounding complexity, really the needle in the haystack in responding to trouble tickets, and of course, solving those trouble tickets in a timely fashion. So what does that look like? Well, you have dozens of vendors, and each of these vendors can look and act very, very differently. Now, you may have vendors that have multiple products within the network, adding to the complexity. Now, what these vendors bring about is devices, lots and lots of devices. So you look at the network, what do we mean by devices? The switches, routers, load balancers, firewalls. So now each one of these devices in the network, we have to tell it what to do. So you create rules. So think about thousands of devices. What do you have? Millions upon millions of rules. Now remember, network operations team, trouble ticket, I have to solve that. How can I solve that? Well, here's how I do it. And that's not very pretty, but this is what our NetOps teams have to do. Yes, of course, they do have certain tools, maybe off the shelf or homegrown tools, but usually it always ends up coming back to here. So in order for your network operations team to really be effective, really be have a good handle on what's happening in the network, you have to know certain information, to really have this information readily available. So start with what you have, how it's connected, where does the traffic go? And once you know that, you better know if it's working and what to change. Now, to give you a little context on this, the previous slide, the amount of vendors, the amount of rules, the devices, we were working with a company, Fortune 500 company, would be considered a very large company, but you think about devices. Now, sometimes you don't even realize how many devices companies actually have, or you may actually have. This particular company had almost 13,000 devices, so let's round it up to 13,000 devices. Remember, we talked about the rules. In order to make these products work, you got to give it rules. Oh, maybe a few million rules. Almost 3.3 billion lines of text in order to operate their network. And then you can see the different changes, firmware, etc. Really, where we are right now, you need a better way. You need a better operational abstraction. How can I perform better and not do things the same old way? So now we're going to talk about, sorry about that. We're going to talk about introducing a mathematical model for your network and what that is and really what it's not. So let's start with what it's not. It's not simulation, it's not emulation, it's not sampling, it's not flow collection. So it's a mathematical graph model. What do I mean by that? So it's really, you have to try to capture the essence of your network, of its behavior at the right level. To really understand about network behavior, a system needs a working model of the complete network, really incorporating how each device responds to every possible packet. And it's referred to as mathematical or behavioral model of the network because each network device is modeled as a transformation function on a set of potential packets. Now, these transformations are essentially algebraic or logical operations that, when analyzed, can verify the complete network design against required policies or behavior. Now, without a mathematical model, you really can't prove network isolation. You don't see the entire network, the context of the entire network. And then constant theme, being much more proactive. In this instance, proactively identify network misconfigurations. So how do we build a network model? We're going to start with a device model. Now, a device model predicts behavior. How to do that? Well, you give it any packet on any port, and it can tell you, here is what the device is going to do with that packet. You fundamentally think of it as nodes plus links. Each node includes rules and links. The device model is the thing that really pulls in all the state and config information of your devices and then can predict the behavior of any packet. And to build it out, the network model is a collection of device models with an actual topology, bringing it all together. Now your model really is going to vary depending on the vendors, which device types, the features you want in this model, and then statefulness. So how do you deploy a mathematical model? Well, architecturally, most implementations look something like this. You're going to need some type of collector functionality, which goes out to the devices and pulls in all of the information needed to build a complete model. Now, this can live in an offboard agent or can live on the devices. The next piece of functionality is the core. This is where device and vendor-specific config state information get combined with knowledge of how to build the device model to put everything in an analyzable form. And then finally, some type of dashboard, some type of user interface that can be shared across teams. Or you can expose this via APIs. So collecting the data, normalizing that data, and then be able to expose that data. So now, building a mathematical model really brings the best ideas of computer science to the field of networking. So let's briefly talk about what makes the model truly unique and truly applicable to modern day enterprise network ops. So we talked before about networks being homogeneous. Well, that's not true. Networks are heterogeneous. So the model needs to support a number of vendors, a number of models, and everything inside of that network. Remember we talked about before, you really need to understand the entire network. Scalability. We talked before about the devices, tens of thousands of devices in a corporate network. Well, you have to be able to scale to that size. Model really needs to scale to incorporate your entire network. And then accuracy. If you really want this model to be the single source of trust for operating the network, it better be correct. If not, it's basically useless. Now, once you have all this, you really have the capability of the model to really be accessible and consumed in a user-friendly way. Now, you can put applications on top of the model. Now, I'll give you some examples of these applications. Go from left to right. Advanced path analysis. This is where you can span both overlays and underlays. A network query engine, if you had the opportunity to query your network like a database. You have an intuitive GUI that really hides the complexity of the underlay and the complexity in an underlay and an overlay environment. And then finally, scalable APIs to integrate with existing workflows and ecosystems. So remember our network operations team. We'll take this full circle. You want to make your network operations teams run better. You want to make them faster, easier, much more efficient, and much more effective. Really want to have empathy for your network operations team and the daunting tasks that they have to go through, and an appreciation for the complexity of operating a modern day enterprise network. So let's look at a few use cases for a network mathematical model. Now, these are potential use cases for large, complicated networks, like service providers, large enterprises, government, and of course, large financial companies. And really, these are all network operations use cases. The people on the ground making, routine fixes and solving problems. You want to search. What is my network doing right now? Can my apps connect? Slow performance? I want to reduce my mean time to resolution. This is the stuff at the front end of a trouble ticket. Verification. Is my network doing the right thing? And do I have the assurance that my network is working correctly? I want to avoid outages. And again, mean time to resolution. Reduce that time. Reduce that window. Change window. Is that change what I expected? And is that change affecting other parts that I did not expect? So why is all this important? Why should you care about network modeling? Because the network matters. Network uptime matters. Operations costs matter. Security matter. Because the speed at which you can change your network absolutely matters. So you think about the business value of intent-based networking, really through a network mathematical model. So anytime you can minimize the human intervention in the workflow, fingers on keys, you can de-risk operations and hopefully avoid network outages. If you can do that, you can increase agility, and really the bottom line is be able to reduce costs. So gave you a brief overview. You could have an hour-long conversation, 2-hour-long conversation of a network mathematical model. So what we've done here at Forward Networks, many of you may be looking at this and understanding, okay, I can do that. I deal with companies all the time and say, yeah, I can have a team of people do that. Build a network mathematical model to make your teams much more proactive and preventative as opposed to reactive. I've had companies say, I don't even know where to start. So really what we've done at Forward Networks is done that for you. We've done the proverbial heavy lifting for you. So I'm going to conclude, I have a few more minutes. I'm going to conclude with just giving you a brief overview of our company and really the problems that we do solve. So the company was started by a couple of Stanford PhDs, and they studied under Nick McEwen. So those that don't know Nick McEwen, he's really known as the godfather of SDN. You saw SDN in Joe Kennedy's last presentation. They also studied under Nick McEwen. Nick had founded Nicira. Nicira was acquired by VMware, which is now VMware's NSX. I bring this up to really show you, or give you an example of the deep networking roots of the founders of the company. Networking, previous slide, networking is very important. When you don't how you know the network's important? When you don't have it. So that's why these gentlemen came up with Forward Enterprise around network verification and network assurance. So remember what we talked about before, readily having this information available to you. These questions you need to have. So in Forward Enterprise, there's a series of applications. First one is called search. When we talked about the use cases, you need to search your network. So what search will do is index the state and config tables for all the devices in your network. And we talked about before, switches, routers, load balancers, firewalls. Take all of this information in. What the end result is, having Google-like searchability of the devices throughout your network. And your search can vary. You can search from very large, vast searches, such as what's in a VLAN. We talk about paths. We talk about the vendors, the devices, the rules. What about the paths? Some of you have very, very large networks. You have trillions and trillions of paths. What about the paths that any packet can take? Well, we can show you the devices in every path throughout your network. Whether it's working, well, verify is the second application. Continuously validate that the network is working the way I expected, constant assurance that it's working the way I want it to work. We supply you with verification checks, both predefined as well as customized checks. Lastly, predict. And we talked about change windows before. When you make a change, did the change work? Did it affect other parts of my network that I didn't want it to? Well, what predict will help you do is really simulate the effect of a proposed change without impacting your production network. Really ensuring a positive outcome of that proposed change. Right now, we're focused mainly on ACLs. So I'm going to talk to you about how we actually do this. So again, we talked heterogeneous networks. It would be easy if everything was homogeneous. That's not the case. We need to comprehend your entire network. And that's both physical and virtual, as well as the cloud providers as well. So currently we're working with AWS and Azure, GCP probably in another, I don't know, 6 or 7 months, mid-year, we'll get something out, maybe by the fall with GCP. Primarily, we gather this information via read-only credentials, SSH read-only credentials. I like to say we're a disruptive technology in a non-disruptive way. So we gather up all this information and we create an abstraction. Remember, we talked about a mathematical model of your network. Remember, we talked before about scalability. So just as an example, being able to analyze 10,000 devices on a single commodity server. Now, the driver in this mathematical model by Forward Networks is something called header space analysis. And that was talked about the founders of the company. One of the founders actually did a thesis on header space analysis. So what is it? Header space analysis is really going to provide you very, very high fidelity on every path to every port on every device that any and all packets can take throughout your entire network. Very, very powerful information. So remember before we talked about the complexity, I keep bringing up paths because trillions and trillions of paths throughout your network now. And when we're making changes or we're trying to make sure the network is functioning correctly, what I like to say is through header space analysis, we give you the answers to the test. You just have to go take the test now. And then finally, we need to give this information back to you in a consumable way. And how we do that is either via APIs or we have a very easy to use user interface. So what we've noticed we can do now is many times you have your teams that are siloed, your network teams, your security teams, or it may be. Well, now we've created a single source of truth for your teams to collaborate on. If there's a problem with a firewall that's preventing traffic to go through, well, now your network teams and your security teams have this single source of truth that they can collaborate on, rather than trying to find the proverbial needle in the haystack and it ends up being a security issue. Hey, can you please help me with this? Well, now you're both looking basically at the same screen. So really, to wrap up what we do here at Forward Networks, it's all about the comprehension of your very heterogeneous, complex network environment, both physical in nature, physical and virtual, as well as the cloud vendors, making it look like one big network. Be able to create this digital twin, this software mathematical model of your network, but be able to do that at scale. And then finally, be able to give this information back to you, expose it to you in a very easy to use format, in a user interface that's probably as easy to use as an app on your phone. So I'm going to wrap up there. Wanted to talk to you about a network mathematical model, what it is and how you can leverage it, but then discuss or present to you how we do it at Forward Networks and the value we can provide for you.